So epoxides we have already looked at forming in our previous section. And remember, our epoxides are going to be those three-membered rings with the oxygen. Oxetanes are going to start looking at other cyclic compounds with oxygens that have more than 3 carbons associated with them. What we are going to see is that the epoxides, those 3-membered units, are going to be more reactive than the oxetanes. The 4-membered units are other cyclic ethers that get even larger, 5 or 6-membered rings. But we will see some reactions. Some of these reactions work with both epoxides and with the oxetanes and the 4-membered ring unit. The first reaction that I want to look at is going to be either, it's a ring opening under either neutral or base-like conditions. Under these conditions, we're going to see an SN2 type mechanism. So we're always going to see the nucleophile come in and attack the less substituted carbon atom. So we're going to have the nucleophile come in at the same time that the ring is opening, our SN2-like mechanism. So we're always going to see the attack on the less substituted side. So if we look at our epoxide and we make it an asymmetric epoxide, under base or neutral conditions, so basic conditions would be something like we have the alkoxide anion, or we would be under alcohol conditions, neutral conditions. We're always going to see that that nucleophile, for here would be that RO minus, is going to come in and break the ring open on the less substituted side. Another way that we could look at neutral conditions with completely neutral nucleophiles is going to be if we use something like a salt, sodium chloride, and the nucleophile now becomes that chloride unit. That neutral nucleophile is going to come in and still attack on the less substituted side. We would still have to have some kind of protic solvent in order to protonate that O unit to make it become the alcohol for us. But the key here is under the basic, the O- conditions or the neutral conditions, we are going to be looking at an attack on the nucleophile adding to the less substituted carbon atom. So if we specifically look at the mechanism, again, it is more of that SN2 type mechanism. The nucleophile, whether it is basic, whether it is neutral, is going to come in and attack the less substituted side at the same time that we see the ring break open. Initially, when we break that ring open, we have an alkoxide anion, which is why we typically need some kind of protic solvent so that we can undergo some acid-base chemistry to get to a final neutral species. So again, hopefully you can see this is an SN2-like mechanism where the nucleophile is attacking at the same time that carbon-oxygen bond is breaking. With this process, we can also use organometallic species to do this same type of ring opening. So things like RLI, organolithiums, the Grignard reagents, the RMGX. So remember, both of these species really behave as that R- in solution, and that becomes our nucleophile. We can also use the CN- unit or the alkyne that has been deprotonated to make new carbon-carbon bonds through this ring opening process. With all of these, having a protic solvent would not work under those conditions, so we would have to initially break the ring open, and then a secondary step would be to follow up with an acid to make sure we get out the neutral alcohol. Another thing that we can do to kind of stop our chain when we open it would be to use a hydride unit. So we talked about hydride, sodium borohydride, aluminum hydride, in order to add a hydrogen to break open the ring. But again, we would have to have a secondary step, follow-up step, to make sure that we get the neutral alcohol after we have broken the ring open. But all of these will also work like that typical SN2 mechanism. So just looking at an example using the Grignard reagent, I would start with the Grignard reagent. That is what would open up my ring. From there, I would have to do what we call an acid workup or an acid wash in order to get to the neutral alcohol in the end versus stopping at the O- in our mechanism. But mechanistically, these would all work the same way. The nucleophile just becomes that R- unit, or it would become the H- unit. We can also open up our rings under acid catalyzed conditions. But under acid catalyzed conditions, it's more of an SN1 type mechanism. So we're going to attack at the more substituted carbon atom. So when we look at this process under acidic conditions, what we will see is that the nucleophile is going to add to the more substituted carbon atom of the epoxide ring instead of the less substituted. So under our acidic conditions with this mechanism, we see a reversal in when we protonate the oxygen, and that's really what's going to change for us why we see SN2 versus an SN1 type mechanism. So through this protonation, we start to see the bond being broken between the oxygen and the carbon atom that is more substituted. And this carbon atom here has the higher partial positive charge. So since it has the higher partial positive charge, the halide that we generated is going to come in and attack that carbon instead of the less substituted carbon. The easiest way to remember that is since it is SN2-like, with that positive charge being on the species, the carbocation is more stable on a more substituted carbon atom, so that higher partial positive charge is going to be on the more substituted carbon atom, which is what allows the nucleophile to come and attack that more substituted carbon atom. So whether we are under acidic conditions or base or neutral conditions will dictate which side of the ring actually opens. So now let's talk a little bit about our oxetanes. Remember, the oxetanes are those 4-membered rings. These need really, really strong nucleophiles in order to open them up. So really the O- would not work. We would need to use one of the organic metallics. We would have to use organolithium or the Grignard reagent in order to see the oxetane actually open. The other rings that are larger, 5 and 6-membered rings, these are actually very stable. They do not break open under different conditions. They're actually some of our common solvents that we use that would be aprotic solvents for us. So one of them is THF, which is our tetrahydrofuran. This is our 5-membered ring with oxygen as one of the members. And again, this would be very non-reactive to any type of ring opening, which is why it is a common aprotic solvent for us. We can also have THP, which is tetrahydropyran. And this is the 6-membered ring with oxygen. And again, it's very non-reactive. It would not ring open under any of these conditions. It's very stable, which is why it is oftentimes one of our aprotic solvents.